The chemical potential of B is equal to the standard state chemical potential of B plus gas constant times temperature times the natural log of B over 1. We don't need it. And so on, okay, for C and D. And if I plug that all in, okay, this relationship up here becomes stoichiometric coefficients of A times the chemical potential of A at standard state. Plus, what I've done is I've distributed the stoichiometric coefficients out. I've multiplied them through by both this term and this whole term here. Okay, so I have stoichiometric coefficient of A times RT, the natural log of A, plus stoichiometric coefficient of B times chemical potential of B at standard state. B, I'm super going to run out of room, I'm guessing. On the right-hand side, I've done the same thing for C and D. Stoichiometric coefficients of C times the standard state, C at standard state chemical potential, plus nu C times RT, the natural log of C, plus for D. And coefficients of D times RT, the natural log of D. There it is. Okay. And now what I want to do with this, I'm going to regroup. I'm going to put all of the standard state terms on the left-hand side. Okay. And I'm going to put all of the terms that have gas constant and temp onto the right. And I'm going to pull those two constants out. Okay. And set them aside. So let's leave that there. So like I said, I want to regroup these so that all of the standard state terms get on the left and all of the terms with RT get on the right, and then I'm going to pull the RT out in front. So stoichiometric coefficients of A times the chemical potential of A at standard state, plus stoichiometric coefficients of B, chemical potential of B at standard state, minus, okay, my product terms, okay, and this is equal to RT, pull that out in front, and I have, let's see, the stoichiometric coefficients of C times the natural log of the concentration of C, plus D times the natural log of the concentration of D. I'm subtracting from that. I'm moving these terms to the right, so I'm subtracting my A term and my D term. A, the natural log of A. And this is plus B, the natural log of B. Oh, there it is. And what I'm going to do in here is I'm going to apply properties of logarithms. So just recall very quickly that the natural log of two things multiplied together can be rewritten as the addition of the natural log of each of them separately. Okay. The natural log of the quotient, such as m over n, would be given by subtraction. The natural log of m minus the natural log of n. And for, if you have something raised to a power, it becomes a multiplication factor, okay? N times the natural log.
Can you scooch the paper out, please?
Maybe. How about now? Okay. And so what you should be able to see in here is that these terms here are going to be able, the stoichiometric coefficients are going to be able to go into, they're in the front right now, and they're going to become a power, okay, raised to a power. And these two things are added together, so they're going to become a product. And we're subtracting these two, so they're going to go on the bottom, okay, as division. And so when I rearrange everything on this side, I have RT. When I apply all my log properties, I have the natural log of the concentration of C raised to the stoichiometric coefficient of C times the concentration of D raised to the stoichiometric coefficient of D over A raised to its stoichiometric coefficient and B raised to its stoichiometric coefficient. Subtraction terms are now the quotient, they're on the bottom. These ones are being added together, they're on the top. Okay. By power law, we move these up. So this whole thing looks a lot like, it doesn't look a lot like it, this is KEQ. Concentrations of my products raised to their stoichiometric coefficients over the concentrations of my reactants raised to theirs. Keeping in mind that the real version looks like this, right? C naught, D naught, A naught, and B naught are actually in the bottoms of all of these. Okay, we're just not including the 1 mole in any of them. And on the left-hand side, what I'm going to do is what I'm going to do is just multiply everything by -1. I'm going to multiply on both sides of this whole relationship. By -1. So if both sides get multiplied by -1, everybody stays the same. There's a negative sign over here now. On the left-hand side, all of these signs flip. So I now have stoichiometric coefficients of C times the chemical coefficient of C at standard state plus D at standard state, and I'm subtracting from that A minus B. These are my products. Recall that these are number of moles. I'm subtracting from that my reactants. This whole thing is standard state free energy change. dG was equal to mu times the change in number of moles. Okay. So if I were to actually integrate all of these things, I would have free energy for each individual piece. But if I take products minus reactants, I now have my delta G.
It's too low.
There it is. So these are my very important equations that I care about a ton and I use a whole ton. I can rearrange this. I think both of these are on our equation sheet. But if you were to divide by negative gas constant times temp onto the left side and raise it to E, we get out of natural log KE2 is equal to E to the negative change in free energy at standard state divided by gas log times temp. What's the units of KEQ? Nothing. It's unitless. This is all molar over molar times mole over molar times, it's all nothing. It all goes away. Okay? And the units of this are going to be joules per mole. This little thing here tells me, this is what's telling me I care about per 1 mole. Standard state means I'm interested in per 1 mole at a time.